In this video, I'm going to define the definite integral. But before we do that, let's take a moment and think back to Calc 1 when we're talking about the derivative of a function. What typically sticks with us is more often the rules, the product rule, the quotient rule, etc., the power rule, how we compute the derivative most efficiently. But before we get to those rules, when we're learning about the derivative, we want to think about what it is we're trying to accomplish, what we're trying to measure, and we need to define it in a way that it's clear that what we have, our equation, does give us what we desire. So if you think about the way we visualize the derivative, imagine I have my function f of x. Let's just sketch something in the first quadrant here. If this is f of x, instead of me trying to illustrate f prime of x, let's assume I want to demonstrate f prime of, say, a. So a is a particular value of x. And what we've come to associate visually with the derivative is that we're trying to find the slope of the line tangent to f at a. So the slope of this red line. So to kind of ensure that what I've written over here, that f prime of x is defined to be the limit as h goes to 0 of f of x plus h minus f of x over h. Well, first of all, I can swap in a for x if I want to look at the definition of f prime of a. And what this is saying here is we can focus on this quantity and how it depends on h. So if I want to think of now a point, let's put it over here. Maybe I'll do this in black as well. A plus h. Then what I've boxed in blue is saying what's the slope of the line that connects this point with this point. And of course, we can visualize that slope. That is an estimate of the slope of the red line. And the idea by taking the limit as h goes to 0 is that as I let h go to 0, my right blue point will become closer and closer to my left one. And we continue to look at the slope of what we term the secant line. So I could consider the slope connecting these 2 points and then these 2 points and so on. And as I send h to 0, then I see that those points are going to collapse onto one another and leave me with the line that I've illustrated in red here. On the other hand, if I say that the derivative of x squared is 2x, it's not immediately obvious why that would give us the slope of the red line. We're thinking about that here. So that's just kind of a reminder of the importance of the definition. We use the definition to then kind of prove some of these simpler formulas that we can use to be more efficient. And the same goes here when we're talking about integration. So at this point, we have the notion of Riemann sums, and we want to build off of that. And I'm going to write down the definition, and in this larger lesson, we're going to focus on using that. But just like we did with derivatives, we're going to use the definition to prove some important results that will allow us to find a definite integral much more efficiently than we're going to be focused on in this particular lesson. Okay, so what I want to point out is we're building off of the Riemann sum notation. One of the things we've seen is that as we increase the number of rectangles, the Riemann sum approximating our area, the approximation improves as we increase the number of rectangles. And that's going to motivate our idea here of thinking, let's see how large we can let n, the number of rectangles, go. And so I'm going to set up the kind of structure much in the way we did with Riemann sum. So suppose f of x is continuous on the closed interval from a to b. We're going to define, much like we did with Riemann sums, delta x to be the length of the interval divided by n. We're going to define xk to be a plus k times delta x. So those are exactly the same way we talk about those with Riemann sums. And we're going to let xk star be any point in the interval closed, from xk minus 1 to xk. I'm going to come back to that in a moment. But with these pieces, then we're going to say that the definite integral of f of x, so let me underline this, from x equals a to x equals b is, first of all, notationally, we're going to set up the definite integral like this. Notice a and b, we call those the limits of integration. Those go the first one at the bottom, second one at the top, and then we call f of x the integrand. We write that there. We're going to define this as a limit of a Riemann sum. So the limit as n approaches infinity of the sum from k equals 1 to n of f of x k star delta x. So what we're taking the limit of, notice, is a Riemann sum. So it's exactly like we've seen before. So by sending n to infinity, we're building off of that observation we made that the approximation for our purposes of the area under the curve got better as n got larger. And here we want to send n to infinity, kind of thinking about the best approximation or the exact answer. So this formula is going to be very important. Again, the connection to Riemann sums is really key here. And just to come back to that xk star notation, a couple things. So this here is simply a Riemann sum. So to go from a Riemann sum to a definite integral, we take a limit. And the xk star notation is just that idea that when you're looking at your subinterval, so xk minus 1 to xk, remember that we get to choose an x value that we plug into the function to get the height of our rectangle. So that choice is left open by putting in xk star. So you could choose xk star to be any point in the interval. So if xk star is chosen to be xk minus 1 in each of the k subintervals, that's what we do when we have a left-hand sum. If you always choose xk star to be xk, that's a right-hand sum. If you always choose xk star to be the average of xk minus 1 and xk, that's a midpoint sum. And of course, what I want to stress here, those are just 3 options. There are infinitely many options for what you could choose xk star to be. For instance, right, it doesn't even have to be in the middle. It could be a random point I'm choosing within this subinterval. But it has to be between xk minus 1 and xk inclusive. So, and the other thing we saw with our min and max Riemann sums is the scheme you choose doesn't have to be the same in each subinterval. So if I happen to choose the leftmost point in this interval, that doesn't mean I have to do that in the right. So essentially, that's allowing for a lot of different Riemann sums, infinitely many. And what's really powerful here is we're saying that while the Riemann sum, what I've boxed in green, might differ, as I send n to infinity, they all converge to the same thing, and that thing is what we're calling the definite integral. So we're going to start to think about how we can actually evaluate a limit like this, because of course that looks very complicated. And then further in the course, we're going to use this definition to prove some pretty powerful results that we'll make a ton of use of throughout the rest of the course.